When looking at the motion of a spring, we will see the same pattern regardless if the spring is being vibrating vertically up and down or horizontally side to side, or in any other direction as well. This motion is often more involved than the motion that we normally look at, for the very simple reason no aspect of this motion is actually constant. For starters, if we look at direction, the direction of the object seems to constantly be changing. At some point it's going down, at other points it's moving upwards. Also, if we're looking at the speed of the object, we notice it speeds up as it's approaching equilibrium and slowing down when it moves away from equilibrium. This means the velocity is always changing in magnitude. It stops when it's furthest away from the equilibrium position. It stops at amplitude and speeds up to its maximum speed at equilibrium, only to slow back down again once it passes equilibrium. This makes sense because the force of the spring, the net force of the system, points towards equilibrium. So when my spring is above like it is now, there's a force pulling it downward, causing the spring to slow down, stop, and then return. But since the force is there, the spring will constantly accelerate. However, once the spring passes equilibrium, the force will push the block back up to equilibrium, causing it again to slow down as it moves further away, stop, and then pull back and accelerate as it goes towards equilibrium, only to switch direction again on the object once it passes equilibrium. This acceleration not only changes in direction, but it's constantly changing in magnitude. The net force of the system is in fact equal to the negative spring constant times the displacement from equilibrium. This means that my mass times acceleration is equal to negative k delta x, again where delta x is being measured from equilibrium. This means as delta x gets larger, a must get larger. For the very simple reason, the spring constant is in fact a constant, and my mass is also a constant. I could even rewrite this as my acceleration is equal to my negative spring constant divided by my mass, all times my displacement from equilibrium. At amplitude, I'm going to have maximum acceleration because I have maximum displacement, and I will have no acceleration in equilibrium because I have no displacement at this point. Please notice my acceleration is a minimum, 0, when my velocity is in fact a maximum. Likewise, my object stops moving at amplitudes. My velocity is a minimum when my acceleration is in fact a maximum. But since my velocity is constantly changing, I would need to have some sort of equation to solve for the motion. Unfortunately, my acceleration is also changing, which means my big three equations of motion, my kinematics, cannot work. We need to use something else. Regardless of that, though, when I am looking at my patterns, it is a very easy trend to see. My velocity is always going to be a minimum when my acceleration is a maximum, and my velocity is always going to be a maximum when my acceleration is in fact a minimum. And the minimum for both of these is in fact 0.